So this will be our second of two videos on diagonalization for Math 1410 linear algebra. In the previous video, we saw that whenever you have distinct eigenvalues, so for an n by n matrix, if you can find n different eigenvalues, then you're guaranteed that you can diagonalize, because each eigenvalue will come with its own eigenvector, and those eigenvectors are guaranteed to be independent, and you can use those independent eigenvectors, collect them together to form an invertible matrix. Now, if the eigenvalues are repeated, you've got a little bit more work cut out for you, right? So in general, you're going to have several different eigenvalues, right? Say lambda 1 up to lambda m, but each one comes with certain multiplicities, right? So the multiplicity of an eigenvalue is just how many times it's repeated in the characteristic polynomial. So these are the numbers k1, k2, up to km, okay? These numbers. And so one of the things we do know is that if I choose one eigenvalue for, say, lambda 1 and I choose an eigenvalue for lambda 2, I'm guaranteed that those will be independent, right? So if I choose one eigenvector for each eigenvalue, I'm guaranteed that those eigenvectors will be independent, right? But what I don't know is, let's say k1 is equal to 3. Right? What I don't know is, can I find 3 different independent eigenvectors for that one eigenvalue? This is the question that's going to determine whether or not we can diagonalize in the case where we have more than one eigenvalue, where we have a repeated eigenvalue. Okay, so the language that we'll use here, and it's fancy sounding language, but it's a fairly basic thing. So we talk about the eigenspace of an eigenvalue. Okay, so the eigenspace is basically the set of all possible eigenvectors, right? We want this to be a subspace, so we throw 0 in. 0 is not an eigenvector, but we need it to be in the subspace. So it's, what is it? It's just, it's the null space of this matrix. It's the set of all solutions to this homogeneous system, right? So in other words, it's the span of the basic solutions to that equation, and the basic solutions to this equation are called the basic eigenvectors, and we'll say the basic eigenvectors for this particular eigenvalue lambda, so we'll call that a lambda eigenvector. Okay, and so what we're interested in is what's often called the geometric multiplicity of the eigenvalue, as opposed to up here, these multiplicities k1 up to km, they're sometimes called the algebraic multiplicity because they show up in a polynomial. So the dimension is the number of basic eigenvectors, right? So this number here, dimension of the eigenspace, this is the number of basic lambda j eigenvectors. Okay, and a basic fact is that for every eigenvalue, there's always at least one eigenvector, so the dimension of this space is always at least 1 if lambda is an eigenvalue. And the maximum possible dimension is the multiplicity of the eigenvalues. So, so if you have distinct eigenvalues, if each eigenvalue only shows up once, then each one of these spaces has to be one-dimensional. But if you have a repeated eigenvalue, if say k1 is equal to 3, then the lambda 1 eigenspace, it might be one-dimensional, it might be two-dimensional, it might be three-dimensional. We don't know which one it is. And if we want to diagonalize, we want to max out these dimensions. We want the biggest possible dimension in each case. Okay. So I don't know if we put that. Yeah. So that's the result here. Okay. So in order to diagonalize, right? So the question of when can you diagonalize in the setting of repeated eigenvalues? Well, you can diagonalize as long as the dimension of each null space matches the multiplicity if they're equal, right? It might be less. If the dimension ends up less, then you can't diagonalize. If it's equal, you can. Okay. One thing that I should, if we're being, let's be kind of honest and open about things here. We've completely factored this characteristic polynomial. If we want to guarantee that we can completely factor, we're allowing for the possibility of complex eigenvalues here. Okay, so we are working over the complex numbers when we make this statement. The other way you can fail to diagonalize is if you're trying to work over the real numbers. You might just be unable to factor your polynomial. That's one of the problems that might come up. Okay, so here's a matrix. I want to figure out if I can diagonalize. So how do I proceed? Well, I find the characteristic polynomial. So let me find, well, I guess this will be the negative of the characteristic polynomial. Last time we did xi minus a. For those of you who like to see it done the other way around, let me do it that way for you guys, okay? A minus x times the identity. So we take our matrix, we subtract x's off the diagonal. Okay, 0, minus 3, 2 minus x, 3, minus 1, 2, 2 minus x. So let's expand along the first row. 1 minus x, 2 minus x, 3, 2, 2 minus x, minus 2, so deleting column 2, row 1, minus 3, 3, minus 1, 2 minus x. All right. So you can see the advantage of doing it this way versus doing, we could have done x times the identity minus a. The advantage of doing it this way is you don't have to worry about flipping signs on the entries of a. The disadvantage is that you're dealing with all these minus x's everywhere, and so the algebra at this stage is a little bit, well, I mean, it's not that much worse, but you have to think a little bit harder. Let me pull that minus sign out. So I have an x minus 1. So here I have x squared minus 4x plus 4, and I'm subtracting 6 minus 2 times, so what do I have here? 3 times x. So minus 3 times a minus x is 3x, 3x minus 6, and then plus 3. Okay. So let's do a little bit of work here. X squared minus 4x minus 2. So this is 3x minus 3. I can pull out an additional 3 here and write it like that. And then again I can do some group factoring, right? I've got a common factor, x minus 1. So that leaves me with x squared minus 4x minus 2 minus 6 more, so minus 8. Okay. And now, and I'll hope that I have not messed things up here anywhere along the way. X squared minus 4x minus 8. Can I factor that? Not so sure that I can. Does it factor nicely? Doesn't seem to factor nicely. Okay, let me pause for a second. Okay, let's resume. Realize where I went wrong. Where did I go wrong? I went wrong because, and this is where I don't like kind of doing it this way versus doing it this way. That minus sign out front caused me a whole world of trouble. When I bring that minus 6 inside, I got to account for that minus sign. That minus 6 becomes a plus 6. So that minus 8 is a plus 4. And there we go. Now I can factor. I get x minus 2 squared. Okay, so we can see that the x minus 2 is repeated, and that means that the lambda equals 2 has multiplicity 2. Okay, Now I want to know if I can diagonalize. So in order to figure out whether or not I can diagonalize, I've got to see how many eigenvectors come along with lambda equals 2. So let's add a page in here. Okay, we'll add one more. Oops, I don't need that. There we go. And let's see if we can figure this out. So when lambda equals 2, okay, I've got to do a minus 2 times the identity. So a was 1, 2, 0, minus 3, 2, 3, minus 1, 2, 2. Make sure I remember that right. Yeah. And I'm subtracting off 2, 0, 0, 0, 2, 0, 0, 2. Okay. So I get minus 1, 2, 0, minus 3, 0, 3, minus 1, 2, 0. Okay. And I try to get this thing down to reducer echelon form. So let's see. So I want reducer echelon form. So I'm going to go 1, 2, 0, minus 2. We can see that row 1 and row 3 are identical, so I get that row of zeros at the bottom. I'm going to get, if I take, I'm going to get 0, minus 6, 3. So I'm going to get 1, minus 2, 0, 0, 1, minus a half, 0, 0, 0. Okay, and so I don't really actually need to write down this. I could write down the solution if I wanted to, but at this point I just do a little bit of analysis and I say, look, there are two leading ones. That means one parameter. And that means one basic solution, which means one eigenvalue. One independent eigenvalue, eigenvector. Okay. And so what that means is that the sort of lambda equals 2 eigenspace, the dimension of the lambda equals 2 eigenspace is 1, which is not equal to 2, and that means that we cannot diagonalize. Okay. One more example. We'll press on. We're probably getting a little bit long in the time, but let's do one more. Okay, so I'm going to do my determinant x times I minus a, x minus 2, 0, 0, 2, x plus 2, minus 2, 5, 10, x minus 7. So expanding along the first row, I get x plus 2, minus 2, 10, x minus 7. So x minus 2, I get x squared minus 5x. I get minus 14 plus 20, x squared minus 5x plus 6, which is x minus 2 squared times x minus 3. So in this case, when I do a minus 2 times the identity, okay, I'm going to get 0, 0, 0, right? Minus 2, minus 4, 2, minus 5, minus 10, 5. And this time, if I take that guy to reducer echelon form, I get 1, 2, 1, 0, 0, 0, 0, 0. Okay, so there is, in this case, one leading one. That means two parameters. So the dimension of the lambda equals 2 eigenspace in this case, E, is 2, which does equal the multiplicity. Okay, and so in this case, I get 2 eigenvectors coming along with that lambda equals 2 eigenvalue. We haven't bothered to find what they are yet. We'll do some examples like that in class. And so the answer in this case is a yes. We're going to get 2 eigenvectors from lambda equals 2. We're going to get 1 more from the lambda equals 3. That's going to be our basis of eigenvectors that we need to construct this matrix P that we use to diagonalize.